are we doing on audio? I think it should be okay. viewing yourself on this camera. Stop. You're muted. Oh shit, can I not, is it not letting you unmute? Okay, let's figure out how to fix that. Participant. Does it work now?
Mhm.
Yes, it works
Yay!
now.
Thank you.
Hello.
Hello.
Very nice meeting you, Liz.
Nice to meet you.
Marcin, here you are. Congratulations. You are now officially co-host with your pretty Vienna background, which I'm amazed at the view you have outside your office. It's so good.
Yeah, and the weather is nice as well.
It's
Actually,
like
the
Wow.
weather is
-3 degrees here.
the
It's like
actual, what,
it's
23?
-3 degrees right
Ah,
now.
-3. Okay.
I am so bored of winter. I would like it to be done, please.
Well, tomorrow is the first day of spring, or the day after tomorrow, I guess. I'm not sure.
Yeah, yes it is. Martin, are you going first or is Lorca going first?
I'm going first.
Great. Can you just make sure that the like chat situation, that the share situation is working out?
I tried.
Just so we can do all the things. Also, like I did get the YouTube stuff to work. I'm very proud of myself.
Hello.
And hello, hello. How are you?
Good. How are you?
Sorry, I'm trying to figure out if this should be I'm making you co-host so that you could also share when things get around, when we get around to that point. I am clearly really, really good at this organization thing. So after all the freakouts and everything like that, I'm sort of just glad that people seem to be able to log in and make this work. So that's really all I've got going for me.
Okay, I think my plan is actually to join the Zoom also with my iPad.
Oh,
So
cool.
maybe it's that needs the sharing.
I think we're okay with having multiple co-hosts. I don't think that there's
Yeah.
any kind of limit, but you know.
Well, I'm also using my iPad, but there is this option to share your screen through Wi-Fi. Have you tried that, Lorca?
No, I think it's too technologically advanced for me.
No, I don't think so. If you go, I mean, you can try it now. I
Can
mean,
we
if
go
you,
back to like transparencies like in the 90s where we had to like
I,
make little things and write them on plastic?
I stop sharing. Now you try to share your screen, and then there will be the option advanced on Zoom.
Uh-huh.
And then the best thing is to choose through Wi-Fi. You have a local Wi-Fi.
I mean, I'm on Eduroam, so I don't think it's gonna work.
You're on, and you don't have a cable because you can also do it through cable.
Yeah, I looked it up, and my impression was
Okay.
that the
Okay.
Zoom
I
app
think
on
it'll be okay
Windows
if we
supports
just
it,
if
but
you just log in at a different thing when the
Okay.
time comes. I
yeah.
think we'll be
Okay. I'm not saying anything anymore.
trying to figure out if the live stream thing is working or if I broke that. Not sure why they asked us to do it, but they did, so I'm trying to follow the instructions at the very least. Hmm. How's everything? How's life?
Busy.
Yeah, I guess the semester started a little bit ago.
Yeah. I'm
I've
teaching
got,
measure theory
oh, measure theory is fun.
in
Nice.
German.
Oh, you see, that's a twist.
Yes.
How's your German?
Good enough to give a lecture, I think.
And isn't that what matters at the end? Okay, do you teach or is it just like a grading situation? What are your sort of your
I don't think I'm
responsibilities?
allowed to teach in the contract, so I don't do any teaching. Yeah.
Yeah, the National Science Foundation has this rule that they only pay for research. So if you have a PhD hired on a grant, they cannot teach.
Honestly, sounds like a good deal to me, but
Yeah.
I'm teaching functional analysis this semester. The unfortunate part of that is that I don't know functional analysis. So I have been doing a very clever little like trying to stay ahead of my lecture by my class by at least one lecture at a time. I am basically there is a very hard limit for this afternoon's lecture because I do not know the material after a certain point. So I have to sort of hope that I have an hour and 40 minutes worth of material, or else I'm just like, cool, I don't know what's next.
I know that situation from other courses, but
At some point, you would think we would get professional enough to not to stop doing that to ourselves, but I at least have not reached that moment.
So what time is it in Boston?
Oh, it's morning. It's 10:50.
Okay, so it's only 5 hours difference with us.
Yeah, it's 5 hours. It's about to go back to 6 hours. By the way, right, like, do we want to keep the seminar at this time, European time? So we'll shift it 1 hour UTC in March, in late March when you do it.
Like, I'm not sure because we have to check that the next seminar, we have somebody that is in Singapore and the other person
Oh,
is in LA. So I think
Oh,
it's the worst combination, right?
we did not think that one out through very well, did we?
Like I discuss with them and they say, okay, like it's going to be very late for me, like 11 p.m. and for the other one, like 7 a.m. So it
Mhm.
worked.
Okay.
But
But
now
we're
we
going to
have to
do that
check.
exact hour to make sure that the things work out. Cool.
Yes, yes.
Just, yeah.
But then,
Well,
like if it's good for the speakers, for me,
I don't care either. It's just a question of sort of getting the stuff done. Anyway, well, we can
we can
deal with
discuss
that
it.
when the time comes. We just need to make the decision at a certain point.
I'm back in a moment.
Okay, you're in India? Marcin was
No,
saying something.
I'm in the UK at the minute. I came back from India on the weekend.
Oh, cool. How was India?
Yeah, really nice actually.
Where were you
I
visiting?
was it was this ICTS place in Bangalore. Um,
Is that where Nishant is, or is that a different
no,
thing?
Trishan is
Trishan's there. Cool. Yeah, very
yeah.
nice.
But yeah, I was quite lucky to be there because the like traveling and everything was just completely messed up like the weekend I flew. So yeah.
I think that might be the understatement of the century.
Yeah.
I'm glad you made it back.
Yeah. Me too.
Many,
So,
obviously, many.
how are we going to do? Maybe I can introduce them and
Mhm.
then, okay, I can do that. And how should I pronounce? Is Marcin, Marcin,
Marcin.
Marcin?
I'm sure that there is a more proper Polish pronunciation, but all of us non-Poles, you have.
I'll do my best.
I guess we'll do 55 minutes questions, quick break, 55 minutes questions.
You said 55? Okay.
Plus
I'm
minus whatever. It's like the just under an hour situation. I'm not sure. Like everybody is perfectly welcome to adjust.
okay.
I think I managed to make it so that people can just join now and we don't have to constantly click and admit.
Okay.
One fewer things for you to worry about.
Mm.
Do we start?
Yes. We start, right?
Yeah.
Okay. Hi, everyone, and welcome to the One Probability Seminar. Today we have the pleasure of hosting Lorca Heeney and Marcin, both from TU Vienna. They will talk about the Ising magnetization field and the Gaussian free field. Please, Marcin.
Thank you, Zoraida, and thank you, Matan, for the invitation. Yes, please stop me and ask questions if there is any. So I'm happy to talk about joint work with Lorca, who's going to give the second talk, and also with Thomas Alcalde Lopez. And the main result is a probabilistic coupling between two objects that I will define, but if you already know them, it's the Ising magnetization field and the continuum Gaussian free field. And if you want to know the definition of this model here, you need to wait until the second talk. So we will use some new percolation model and Lorca will define it. The idea for my talk is to give the background and the motivation maybe, and at the very end state the result. The result needs a bit of an introduction. So I will start with some short motivation from the outside of probability theory, which is from CFT. And then I will talk briefly about the GFF itself. So it's a conformally invariant field, very important in sort of modern probability theory. And I will define something which is maybe less known. It's a geometric object associated with the GFF, namely its two valued sets. After I've done that, I will talk about the Ising model. So I'll go to the discrete. I will define the Ising model, say something about the critical point, expected conformal invariance and proved conformal invariance, and I will talk about the percolation model which is associated with it, the so-called FK Ising model, and the relationship between these two. So there is a coupling between the percolation model and a spin model, which is the Ising model. And then I will describe a result from more or less 10 years ago about a joint scaling limit or a scaling limit of this geometric representation of the Ising model and the magnetization field. So the result is something in the continuum which describes a field which is conformally covariant. It is the Ising magnetization field, and it has some geometric description. And after I've done that, I will tell you what our main result is, because the structure of our main result is very reminiscent of this classical result by now, but it involves a different geometric representation which ties it to the GFF. And as we know, this connection has not been expected or predicted, so we are quite excited about this result. And if there is any time, probably no, I will tell you about some conjectures that we make for other discrete models. So what's the motivation from CFT? Okay, so what is CFT? It's a special type of quantum field theory, which I will not define because I think it's a problem to define it actually in math. But it's a type of QFT, which is invariant which has some conformal symmetries, and it plays an important role in different branches of physics. For me, the important part will be models of statistical mechanics at criticality, and particularly in 2 dimensions where this conformal invariant structure puts a lot of constraints on the system, and then we can say much more than in other dimensions. And what are the basic objects that people are interested in CFT? These are correlation functions. So these are some functions of points in space-time, if you like, of fields which are not well defined at this point, and they should physically encode or describe the statistical correlations between some fields fluctuating in space-time. The problem is that it's not clear what this fluctuation should mean, because most of the time it's very hard to define these things probabilistically. And okay, the fact that it's a CFT puts a lot of constraints on these correlation functions. In particular, if you look at 2 points in your space and you look at the correlation of the same field at 2 points, the so-called 2-point function, then it always has this form, which is a power law with some exponent, which is the scaling dimension. In physics, it's called delta, I guess. And the fact that the system is conformally invariant always imposes this structure, for example, on the 2-point function. And what is the interpretation, say, in probability, that there is no characteristic scale of the system, or the system is scale invariant. Okay, so that's something that will also pop up in the Ising model. Okay, so what are these fields? Actually, we can study the correlation functions, but do these fields actually exist as random objects or not? And an interpretation is that they are not actually pointwise defined because of quantum fluctuations. So you should think of these objects as generalized functions, which cannot be evaluated at a point, but rather at a smooth test function. So you can feed a test function to this object, and sort of what it does, it integrates the field against this smooth test function. Okay, so here this is not defined because O of X is not defined, but okay, this is sort of an intuitive definition of what that object should be when we talk about it mathematically. And if you translate it back to these correlation functions, what it should be is that if you feed, okay, so if you feed it a test function, it should give you some random number, a random variable. If you have a probabilistic definition of these fields, then you can compute the expected value of the product of these random variables, and that should be given by this integral of values of the functions against this correlation function. So this acts as a correlation kernel, actually. So you can make sense of all of that, not in terms of real random functions, but generalized functions which act as distributions. So their arguments are not points, but test functions. All right, so that's sort of the physics setup and the interpretation in terms of probability. And one of the important questions, and often difficult question, is that if you say have a set of correlation functions, can you actually can you construct a random field, which is a random generalized function, with the property that these correlation functions satisfy this property here? And our result is somehow contributing to that understanding. Another question is, if you have two sets of correlation functions for two fields, can you realize them jointly on the same probability space? Is there a coupling between these two fields? And what we do is we define one instance of such a natural coupling. And this coupling will be between the Gaussian free field. So the Gaussian free field is something which you can actually quite easily construct. So this is the sort of special case where you don't have problems defining this random generalized function because it's a Gaussian field. Okay. So what I will always have, it will be a domain in the complex plane. So it can be, suppose, any simply connected bounded domain. We can think about something like that. And then you study the Brownian motion in this domain, which is killed upon hitting the boundary, so with Dirichlet boundary conditions. It has a Green's function, which is this GDXY, and out of that you can produce a Gaussian field. So it's a random generalized function which acts on test functions supported in this domain D, with the property that these random variables that you get when evaluating against the test function, these are Gaussians with mean 0, and with the covariance whose kernel is this Gaussian Green's function, the Green's functions of Brownian motion. So since it's a Gaussian field, it's enough to give you a second moment, so the rest of the distribution obviously is given by the covariance. And in this case, if you know this Green function, it doesn't have a paralodic behavior, it has a logarithmic behavior, so in some sense, for this field, this exponent delta is 0. So the 2-point function of this field behaves logarithmically, not as a parallel. And okay, here is a picture. This is some random function, actually some simulation. You can make sense of this as a function in different ways. You can discretize this model. You can convolve it with some smooth function and regularize it, and then you can produce such pictures which sort of show you how this should look like, how this fluctuates. Okay, so this is a very central object in modern probability theory, or at least in statistical mechanics at criticality in 2 dimensions, and it pops up in many places. It is conjecturally, in very few cases, proved to be the scaling limit of height functions. Height functions are sort of fluctuating statistical systems of statistical mechanics where the values of the spin or the variable are integers and they interact locally with each other. And okay, these objects are well understood. They have 2 phases, localized and delocalized. And in the delocalized phase, when there is lots of fluctuation, the scaling limit of these systems should actually be the GFF. And that's somehow an analog of what we have in 1 dimension. In 1 dimension, you have the Donskir's invariance principle, which tells you that scaling limit of any random walk with finite variance is Brownian motion. So GFF is somehow an analog of Brownian motion if you think about 2-dimensional time in some sense. It's a conjectural scaling limit of many discrete objects. And then it's the underlying process of something called Gaussian multiplicative chaos, which is a type of random area measure, and this then in turn is the base of this very active field called Liouville quantum gravity, which has deep connections to discrete models as well, like random maps. And so on. GFF is also at the heart of something called imaginary geometry. It's a theory developed by Scott Sheffield and Jason Miller, where GFF is coupled to many versions of the Schramm-Lerner evolution, the very influential process which describes scaling limit of models of statistical mechanics. And there is something called bosonization in physics, which predicts a connection between the GFF and the Ising model. But the predicted connection is different than what we have. It's a bit more vague if you think about it in terms of a probabilistic interpretation. So our result adds to this list. And we show that actually if you have a GFF in the continuum modulo a sequence of independent coin flips, this process encodes exactly something which is called the Ising magnetization field. So we make this bosonization connection a bit actually more concrete from the probabilistic point of view. Okay, so this is the process. It's important to understand it. It's not a function. It's a generalized function. But nonetheless, there is a very beautiful theory developed by Aru, Sepulveda, and Werner, and then later studied by Aru and Sepulveda. It's the theory of two-valued sets of this object. So imagine you have this domain. Here is the disk, and you study the GFF with Dirichlet boundary conditions, meaning that it's zero outside, say. And then fixing two constants, you can ask yourself, okay, if this was a function, you could easily define then a subset of your domain where the field has values between minus a and b. That's why it's called two-valued sets. It's minus a and b. It's the set of points where your field is in between those two. And then you look at the connected component of that set, which touches the boundary of the disk, which in this picture, which is obviously not a simulation, but just a drawing, is in gray. So you can see that, suppose that you have a random function with boundary value 0, and then this gray area is everywhere where the value is between minus a and b. And then you can think of exploring the domain, and the first time you hit the value minus a or b, so in this case it's b, you will see some loop which bounds the region where the function is exactly equal to b. Okay. Sometimes when you explore, you hit a loop which with value minus a. So there is two types of loops, with value b and minus a. So this would be all very nice if this was a function, but GFF is not a real function. But nonetheless, you can define a set of loops which play the same role as level lines as if the GFF was a function. So the definition goes actually through some Markov property. So this is the only set of loops such that if you condition on the outside of the loops, for every loop there is a value b or minus a, and inside the domain encircled by the loop, condition on everything that's outside, inside the domain encircled by the loop, you will see an independent copy of the GFF, but with boundary conditions given by b or minus a. Okay, that's a Markov property, and it turns out that this Markov property uniquely characterizes this set of loops. So if you have an instance of the GFF, you know where these loops are. These are measurable functions of the GFF itself. So this is a very nice family of loops parameterized by these two levels, and the height gap between these two levels is b plus a. Okay, now if I denote by L minus AB the collection of actual loops, so the boundaries of these regions where which are bounded by this gray area, this is a loop ensemble. So it's a collection of loops in your domain which is random, and it's also conformally invariant. So it connects to the CFT picture. Since the GFF is built out of Brownian motion in the domain, and since Brownian motion is conformally invariant, the GFF is conformally invariant. So if I say start with a GFF in the disk and then I map it by a conformal map to the disk itself, the law of the map thing will be the same as the one before. And because of that, this conformal invariance is inherited actually by these loops as well. So this is a collection of conformally invariant loops that will play an important role in our main result. Okay, and there's many things known about these loops. So, for example, they only exist if the gap is big enough. So there is some threshold lambda, which is an explicit constant, such that if the gap between the two levels is bigger than that thing, this object is well defined, and below it's not defined. And the smallest sum of a and b is 2 lambda, which is called also the arc loop ensemble. In this case, these loops are sort of they look different than in this case. For example, here the gap difference is 4 lambda, and what you see is that, for example, the loops on the right, none of them touches the boundary of the domain, and these loops also don't touch each other. And here, actually, every loop touches the boundary and the loops touch each other. So this is the value for lambda is actually the first value if you increase the gap, where you start seeing loops which don't, such that none of them touches the boundary. So it's somehow a critical value. And if you have values in between 2 lambda and 4 lambda, these loops will, some of them will touch the boundary and some of them will not touch the boundary, and they will touch each other. So these things have been studied in the literature, and I will come back to this later. We will use these sets to describe this new coupling in the continuum between GFF and the Ising model. Okay, so what is the Ising model? Probably we all know it, but let G be a graph, connected and planar. In this case, just a subset of the square lattice. And the Ising model is a random assignment of plus minus 1 spins to the vertices, and the measure is governed by this Boltzmann weight. So usually one has a beta here and says inverse temperature, but to match it with our paper, I say it's a J, and it's the coupling constant. So if J is 0, everything is independent, so it's like infinite temperature. And if J is infinite, basically, if you have a finite graph, then all spins point in the same direction, which is plus or minus 1, and it's like 0 temperature. So this model has more than 100 years. Okay, before I say that, I also say that you can consider plus boundary conditions. So this definition is free boundary conditions. I don't impose anything on the boundary. And if you have a graph in the plane, you can think of the outer boundary that it has, and forcing spins to be plus 1 on this outer boundary results in an Ising model with so-called plus boundary conditions. So it's just this measure conditioned to have spins on the boundary to be equal plus 1. Okay, so it's a very well studied model. Lots of things are known about it. Our setup is the square lattice, 2 dimensions. So the first thing is now not that difficult to prove, is that, you know, at high temperature or low coupling constant, the model is totally disordered. So it sort of looks like a TV screen from when I was young, maybe. And then if you think about some quantity that you can measure in the system, like the expected value of the spin, say in the middle of the box, here what I did is I put white boundary conditions. So white says plus and blue is minus. You don't really see what the boundary condition is here because it's so disordered that you forget it immediately. But if you put plus boundary conditions, the value of this expectation, which is just a spin in the center, is not 0. I mean, for the free boundary conditions, there is a symmetry. Flipping all spins results in the same energy. So the 1-point function is 0. We break the symmetry by putting plus boundary conditions. It makes it more positive because it wants to align with the boundary. But it's still very small if this box is, okay, if this is lambda n, meaning that it's a square of side length n, in this regime where you're small or smaller than some critical point, and this 1-point function will just go to 0 exponentially fast in the size of the system. You forget the boundary conditions at an exponential rate. So this was known from the start of the Ising model. This is the low temperature phase, which was known only 10 years later, maybe, when Pyros proved that this exists. So this is the low temperature phase, so big coupling constant. Again, wide boundary conditions, but now we see that the boundary conditions have a drastic influence on the system. Everything is white, basically, with very small, tiny islands of blue, of minuses. So this is the ordered phase, or the symmetry of the phase of spontaneous symmetry breaking. And in this case, it's also sort of easy to prove that if you look at this expectation of the spin in the middle, it just stays uniformly positive because the system remembers the boundary condition at all scales. So high temperature, low temperature, and there is only one point where there is something in between, which is the critical point. And okay, on the square lattice, we know exactly what that is. This is due to the exact solvability of the Ising model. And in this case, we also know that the 1-point function goes to 0, but this time it has an exponent in it, which is sort of like this exponent delta in the CFT motivation. And it's a famous exponent of 1/8, which was computed for the first time, maybe by Onsager and Yang in the 50s, I think. And this is obviously this is a sign of criticality, no of scale invariance and so on. And if you look at the simulation, you actually see clusters of blue at all scales. So there is no characteristic scale. It seems like you see really clusters of any possible size in this picture. So that's the thing that's the picture that we know for many years now. And recent progress has established more very fine properties of this. For example, you can describe the system as a collection of random loops. So you can draw the boundaries between plus spins and minus spins. And if you put plus boundary condition, this will just give you a collection of random closed loops in the domain. And you can ask the question, what is the law of these loops if your system sort of gets finer and finer? So for example, you keep the size of the box fixed in the plane, but you approximate it with meshes which are smaller and smaller at criticality. So to say what that result is, I must make a small detour, which is the definition of conformal loop ensembles. So what are these objects? These are random collections of loops in a domain. Here it's a disk with two properties, which you can crystallize as one property called conformal restriction property. They are parameterized by a parameter kappa, which is the same kappa as in this Schramm-Loeffner evolution. And they were defined by Werner, Sheffield and Werner, and Miller and Sheffield in different works for different regimes of kappa. And for example, it's known that this picture that I had here, these loops at criticality for Ising, they correspond to kappa equals 3, which is, here it's a simulation due to Jason Miller. I didn't write it here. So it's a known result already of 10 years that if you look at the collection of loops, take a scaling limit, it will be given by this CLE3 process, and it's a result of Benoit and Ongler, and is built on these breakthrough results of Smirnov, who first proves conformal invariance of the critical Ising model in 2010. There is a second regime of these conformal loop ensembles. For kappa bigger than 4, you have loops which are, you don't see it in this picture actually, but for kappa smaller or equal 4, all these loops will be simple. They will not touch each other and they will never touch the boundary. And for kappa bigger than 4, strictly, these loops will touch each other, will be non-simple, and will touch the boundary of the domain. So here is kappa equals 6, and that also corresponds to a different model of statistical physics where we consider independent Bernoulli percolation, and this was also proved in the last 20 years that interfaces in that model converge to CLE kappa. Okay, this is the critical point, kappa equals 4, and it's a famous result of Miller and Sheffield that if you look at this collection, kappa equals 4, it has the same distribution as this, this should be L actually, the set of loops in this two-valued set. So I told you about two collections of conformal invariant loops. One of them is these two-valued sets. The other is CLE kappa. It happens for some reason to be true that these two collections have a point in common, which is kappa equals 4, and this two-valued set with gaps -2 lambda and lambda. And we will come back to that later. Okay, there is another kappa which is important in this story. It's kappa equals 16/3. And to get to kappa equals 16/3, I have to define another model of statistical mechanics, which is this so-called FK Ising percolation. So now you look at the same graph as for the Ising model, but you're not considering spins on the vertices. You're considering either open or closed edges. So in this case, this pink thing is an open edge of my graph, and the law on these open and closed edges is given like that. For every open edge, I pay a multiplicative price, and this price is connected to the parameter of the easing model. For every closed edge, I pay the price 1 minus p. So were it only for these two terms, that would be the Bernoulli percolation model. FK easing model is reweighting that by 2 to the number of clusters, where cluster is a connected component of these open edges. Okay. And okay, this also has two types of boundary conditions. Either every vertex on the boundary is considered a separate vertex when you count clusters, or every vertex on the boundary is considered as one common vertex, and then you think of this as a wired boundary, and then the model has plus boundary or wired boundary conditions. And there is a very famous coupling going back to the 80s or even to the 60s maybe, which says that if you start with this percolation model, and I will be talking mostly about plus boundary conditions. So suppose you start with the FK model with wired boundary conditions, and you do the following. So there is this cluster of the outer boundary, which is this one, and then you say every vertex which belongs to this cluster gets spin +1, and then for every other cluster, you flip a symmetric coin and you decide whether all vertices in that cluster will be plus or -1. And when you do that, you get a spin configuration by construction. Everything on the boundary will be +1. And this coupling is just saying that the thing on the right will be the easing model. Okay. If you start with FK random cluster on the left with this parameter p equals 1 minus e to the -2j, then on the right you will get the easing model. And this is a starting point for this classical now result that I will describe you about taking a scaling limit of this. And at this point, you can, this has been known for a long time. And at this point, you can ask yourself this question: is such a percolation process unique? Okay, I will say that the percolation process has the Edwards-Sokal property. If you sample it and then you do this procedure with assigning spins uniformly for every cluster except for the boundary cluster when it's 1, if you get an easing model. Can you have more than one percolation processes with this property? So it's a natural question, and after a moment of thought, you can easily see that there must be more than one, and actually there must be a huge number of percolation models with this property. For example, if I have an edge in a cycle, I can always remove it. Okay, if I remove an edge in a cycle, I don't change connected components. So I can always delete all edges which are in a cycle. This is giving me a different percolation process, which will give me the same spin model. The distribution will be the same on the spin model side. But you can say, okay, this is very unnatural. I'm doing FK and then I'm erasing something, and okay, what is that? All right, so that's fair enough. But what we are gonna do what we did in our paper is we actually found a very natural process which has the same property, but it doesn't come from FK, okay? We found a natural process which is defined through something called random cluster model, random current model, and we worked with that, and Lorca will say something about that. Okay, one thing which is a consequence of this coupling is that you have a representation for correlation function. So if I now compute the correlation function or the 1-point function of a spin at site X, if you think about it, this is the same as the probability in this FK model to be connected to the boundary, okay? If you're not connected to the boundary, there is a +-1 chance, equal chance that you're +-1, so this contribution vanishes. And the only chance that you're seeing something non-vanishing is when you're connected to the boundary. So the 1-point function is the same as the probability of being connecting to the boundary in this percolation process. So for example, here. So this gives you somehow a dictionary between correlation functions of the easing model and some geometric properties of this percolation process, which has been very influential in the study of the easing model. And this FK process has very nice properties. For example, it has the FKG inequality, which means that it's positively associated. So that just means that if you see somewhere open edges, this makes other edges to being open more probable, okay, in some sense. And it also has a property which is called duality in 2 dimensions, meaning that if I start with the percolation this pink one in the plane, and now I consider the dual graph. So every face of my original graph is now a vertex, and draw a blue edge whenever there wasn't a pink edge crossing it. This gives me a bond percolation on the dual graph. This is a classical construction in planar statistical mechanics. It turns out that this blue thing also has the same law. So it's an FK process associated to an easing model on the dual graph. Free boundary gets mapped to a wired boundary, and there is some relation between coupling constants, which makes it work. So the coupling constant on the dual graph, J star, should be related to J in that way. So it's a model which is very nice from the percolation point of view, and also it's very nice because it's self-dual, and this allowed people to use it to the full extent in 2 dimensions. We will have a model which has none of these 2 properties. It has something of FKG, but basically it doesn't have self-duality for sure. Okay, so to state the result at the end of the talk, I need to look at the easing model not geometrically as these loops, not at a point as a single spin, but as a generalized function. So I think of a configuration as just a signed sum, where the signs are the spins of the delta masses. So I can feed it a test function f defined on the vertices, and it just gives you this signed sum of the signed sum of values of this function. And if you combine this interpretation of the easing model with this geometric sort of FK representation, which was proposed by Kamiya and Newman, you have now a geometric representation of this generalized function. So I can sample an FK easing model, and for every cluster CK of this model, so every connected component defined by the open edges, I have this is a subset of my graph. And then on every such connected component, I can define sort of the cluster measure or the counting measure, which is just the sum over the vertices in the cluster, which is the same as the indicator function of this cluster. And the field writes basically as a signed sum of these cluster measures. So they propose to study this representation of the field as a generalized function, and they took a scaling limit of that. So what is the scaling limit about? I will start with the domain as before. I approximate it by Z2 lattice times a small mesh size. So delta is the distance between the 2 lines. It's a small mesh. I consider a critical easing model. So J is equal to this critical point that I defined, and it's actually the self-dual coupling constant, which solves the equation J equals J star. And what else? Okay. If you think about the model as pointwise defined for this, say, expected values of products of spins or correlation functions, this was proved to converge at criticality in this landmark work by Chelkak, Ongler, and Zurov, 2012, who also developed the techniques of Smirnov, who proved the first conformal invariance result for the easing model in 2010. So in particular, what we know is that the 1-point function, which is the probability of being connected in this FK percolation model, decays as delta to 1/8, which is in agreement with this prediction from the 50s. Okay, and so this was known before the result that I want to introduce now. So again, about this duality of FK clusters, if you start with the FK model, you draw this dual percolation process, and now you can just draw a collection of loops. Okay, we like loops, so we want to draw loops between pink and blue. And in the discrete, if you know these loops, which separates the primal and dual clusters, you know everything about the configuration. You know where the blue edges are, and you know where the pink edges are. So the model is fully described by this collection of black loops. And it was shown by Kempinen and Smirnov in 2016 that these loops converge to the CLE 16/3. So 16/3 is bigger than 4. So it's this regime where you have loops which are touching themselves, each other, and the boundary. And okay, This collection of loops converges to a nested version of that CLE, because here we have nested loops, so there are loops within loops. And what's a nested version of the CLE? You sample a CLE in the disk, and then in every loop defines a new domain, and in that domain you sample an independent copy of this process, and you continue ad infinitum. Also that is the definition of the nested version of the process. And this scaling limit of these black loops at criticality was established also 10 years ago. Okay, we know that loops converge to CLE 16/3 and that these loops encode fully the clusters of Fk, and the clusters of Fk somehow geometrically encode this magnetization field. Okay, in the discrete, the clusters of Fk live actually between the loops, okay? So if you look at this picture, the first cluster of the boundary, which is the pink one, it's actually the space between the boundary itself and these outermost loops, okay? So if you think about it, what should be the scaling limit of the cluster itself, not of the loops? It should be the space in between the boundary of the domain and the first level of loops. And this is called either the carpet or the gasket, depending whether you're below 4 or above 4. And don't ask me why the name, because I can never remember which one is which. But this is correct, I think. And okay, so having these loops in mind that they converge, we expect that these clusters themselves converge as sets to these gaskets. So in the case of the Fk percolation, these clusters should converge to these clusters in the discrete should converge to the gasket of CLE 16/3. Okay. There's lots known about these sets. For example, it's known what the Hausdorff dimension of these gaskets are as a function of kappa. It's a very simple formula, but it's not simple enough to notice the following property, is that if I compute this formula at kappa equals 4, which is the left-hand side, and we will use these sets in our representation, you get that this dimension is 15/8. And 15/8 is 2 minus 1/8. And 2 is the dimension of the ambient space, the plane, and 1/8 is the scaling dimension of this field that we consider. So this thing all works out very well. And if you do the same thing for the 16/3 kappa, you get the same number. So I'm not sure if this was noticed before, but we sort of give a new interpretation of the fact that there is 2 kappas for which these sets have the same Hausdorff dimension. Okay. So hopefully now this result makes sense. That's the classical results that I wanted to mention of Kamiya, Gaba, Newman, and there was a second paper of Kamiya, Konine, and Kiss, who proved that if you consider this Ising magnetization field considered as a random generalized function scaled properly, which is again 2 to the delta to 2 minus 1/8, which is dimension of the ambient space minus the dimension of the spin field. Okay, that's the generalized function in the discrete. It has this discrete representation using Fk. So I have scaled the measure of the cluster of the boundary without any sign. The cluster of the boundary is called C0, and the rest of the clusters come with IID coin flips. So this is just a discrete picture. They prove that this thing converges to a continuum field, which we denote phi plus. And they proved also that this representation converges, meaning that whatever you expect from this story so far is true, meaning that these clusters converge, these cluster measures converge to some measures on the gasket of the CLE 16/3. Yeah, for example, this first measure is some measure in the continuum, which is supported on the gasket of CLE 16/3. And it should be thought of as some type of area measure of this gasket, even though it's a fractal set. So they arrived at this geometric representation of the continuum magnetization field. And this is stated again. So here, the gray thing should be the scaling limit of the first cluster in our domain. Its dimension is 2 to the minus is 2 minus 1 over 8, sorry, which matches the dimension of the magnetization field. And if you think about it, each cluster in the discrete converges to some gasket in the continuum in this nested CLE 16 over 3. So there will be nested versions of this, there will be nested loops in this continuum picture, and you will look at gaskets of loops within loops, and these will be playing the role of discrete clusters in the discrete representation.
Marcin, can I interrupt just real fast?
Yeah.
You said that the convergence is in one of these H Sobolev spaces.
Yeah.
Should we read into the particular exponents there, or is this like the thing that needed
That's a
to
good
make it
question.
work?
Thank you. That's a good question. It's not an optimal exponent. It was then improved to, I think, minus 1 over 8, if I remember. Maybe Lorca can correct me, which should be the true one. So in that paper, they didn't care about the optimal exponent.
But is there
This is
so
just
the exponent there is meaningful because it's exactly going to be the 1/8 that you see there in the sort of the Ising magnetization field if you do
I
it
think that's the
right.
case. They just cared about some type of convergence in any Sobolev space, so they didn't care about the exponent, the
Thank you.
regularity. Thank you for the question. It's important. Okay, so this is the geometric picture, and all right. So out of that, we know that phi is a conformally covariant field, and this is it's non-Gaussian. That's what actually they also proved. It is Gaussian if you do the same thing in dimension 4 and higher. These are seminal results from the 80s and recently by Dumesnil, Copan, and Eisenman. So 2 and dimension 2 is special. This shouldn't be Gaussian as well in dimension 3. The most technical part of the argument is convergence of these cluster measures, which I think Lorca may talk about a bit later. And from that whole story, it's clear that if you have this nested CLE 16 over 3, this fully encodes the Ising magnetization field if you just add to it an independent sequence of coin flips. Once you have a collection of CLEs, once you have the nested CLE 16 over 3, you can get out of that the Ising magnetization field. Okay, I have 10 minutes to state our results. I spent so much time to introduce everything to make a comparison with their result and obviously to define all these objects. So our result looks, if you look at it, it looks the same. We have a representation of the Ising magnetization field in terms of continuum objects, which are somehow clusters or sets in the continuum. And there are measures on these things. And also they come with the independent coin flips in front of them. The external cluster will always get plus sign as before, and the other ones will get independent coin flips. The difference is that these sets are different, and they are obtained from a GFF. Okay, the GFF is hidden here at the last word. So once you give me a GFF, I can recover all these continuum sets or these continuum measures, and you can build out of that and this Ising magnetization field. And okay, we can actually encode 4 Ising magnetization field out of 1 GFF. It connects to this thing called bosonization, for which I will not have time probably to explain. There is 2 independent fields with plus boundary conditions and 2 independent fields with free boundary conditions encoded by a single instance of a GFF. Okay, if you ask me later, I can say something about that. All right, so, okay, what follows from our result that maybe GFF is even more universal than we thought, it actually also encodes this other fundamental object, which is this GFF, the Ising magnetization field. It is an extension of the bosonization phenomenon coming from physics. And also, we learned when we were finishing the work that this was also conjectured by Yuan Aru and Titus Lupo at the same time, who established this identity at the level of second moment. So not the full distribution, but they proved that if you look at the two sides, Ising magnetization field and this sort of sum of sign measures, that they have the same second moment or 2-point function. All right, okay. What are these sets? So maybe that's the last thing to say. Like, what is the composition? You start with our domain is the disk. The first thing you do, the C0 cluster, or in the continuum, is just the carpet of this two-valued set with values minus 2 lambda, which, as I said, is the same as CLE4, which has the same dimension as CLE 16/3. And that's why it makes sense. We encode the same spin magnetization field, so these clusters must have the same Hausdorff dimension, and for some reason they do have the same Hausdorff dimension. So what you do is you sample this thing. There are certain loops, they don't touch the boundary because the values are such that they don't touch the boundary. Some of them have value 2 lambda when you go inside and explore the field further. Some of them have value minus 2 lambda. That's the first level of the construction. And then what you do inside every loop, you sample a different two-valued set. Okay, why? I will not have time to explain. This is coming also from different work, different results about scaling limits of double random currents. But in the picture, you can see that qualitatively these loops are different because they touch the boundary and they touch each other. And okay, you can see this in this gap. Here, the gap is actually 2 square root of 2 lambda. It's not 4 lambda as for the CLE4, but if you sum these two things, it's 2 square root 2 lambda, which is strictly smaller than 4 lambda. And I said that in this case, you will have loops which touch the boundary and touch each other. So you do the second step, and then you go inside the loop again to define the next layer of clusters. So this is C0, the gray thing, and then you define C1 and C2 and so on iteratively in every of these holes. So they also have some values on these loops as before. And what you do inside them, you do a CLE4 again. And this is the step where you repeat. So you do a CLE4, which is A minus 2 lambda, 2 lambda. Inside every hole, you do this other two-valued set. And inside every hole of that two-valued set, you do again CLE4, and you repeat ad infinitum. You pick up a cluster whenever you do a CLE4. So these clusters will always be carpets of CLE4 nested in these loops of the two-valued sets, and this defines you this collection of clusters in the continuum. It's hard to, okay, it's better to do it with pictures, with formulas. Here I put the next iteration. Obviously, I cannot draw this infinite iteration. But anyway, the difference with the picture from before is that these are different sets. And as for CLE 16/3, when we are iterating, we're always sampling the same process. Here we alternate between two processes. One of them is CLE4, and this one has the right dimension of the carpet, which is the dimension of the spin field. So that's the statement of our result. And the starting point of the proof is a new percolation process, which has the same Edwards-Sokal property with the Ising model. It is built out of double random currents, if you know what these are. And we use scaling limit results of double random currents, where we proved with Hugo Dominique-Copen and Wei Qian that they converge to these two-valued sets. There's problems with the standard approach from 10 years ago in that this model has no FKG in the classical sense. It's not self-dual, and we have to go around that. We have to prove things like RSW estimates and the existence of the incipient infinite cluster for omega. So maybe Lorca will say something about that in his talk. I just want to say that this model fits into a broader class of models called Ashkin-Teller models. I mean, the Ising model is a special type of the Ashkin-Teller model. The Ashkin-Teller model has two parameters, J and U, where U is 0, it's just two independent Ising models. And in this model, you can study sort of two fields associated to it. Either you study the single spin sigma, or you study the product of two spins. So you have, at each vertex, you have sort of two spins. If U is 0, these are just two independent Isings. If U is non-zero, these are somehow two coupled spin configurations. You call simply sigma the magnetization field, and the product of sigma and sigma prime is the polarization field. And there is a critical line that has been established rigorously, also mathematically. And there are predictions coming from physics about what these things should be. And these things should be in the scaling limit at criticality related to the GFF. This is the so-called bosonization phenomenon from the 70s and 80s in the physics literature. And what follows from these predictions, and some of these things are proved, but only in the case of the Ising model in terms of the spin fields. Actually, there was a recent breakthrough for the height function converges to the GFF maybe last week. For the general case, so we are excited about that as well. But for the convergence of spin fields, this has only been proved for the Ising model. And then when you see this Ashkin-Teller model, you see that naturally you have actually two configurations, polarization and magnetization, and they actually behave differently in that this polarization field should be in the scaling limit described as a local function of the underlying GFF. It's a cosine of the GFF. One has to define what that means, but it's not that difficult to define. And it has been predicted that these polarization fields in the scaling limit should be random generalized functions, which are nice local functions of the underlying GFF. And there is a prediction coming from physics, which is saying something about the magnetization field. But if you look at the physics literature, at least as I understand it, it's only about something called a twist field of the GFF, which is not actually a random variable. There is no interpretation of this twist field as a random variable of the GFF. It's a sort of a disorder insertion in terms of statistical mechanics. It's a ratio of partition functions where on top you have a GFF with some disorder, so you actually change the state space of the model divided by the partition function of the model without this disorder. So it's really not clear how to make sense of that in terms of true fields with expectations and so on. And our result is actually giving meaning to that these objects as true expectations of true fields of the GFF. And there is one thing in common with the prediction from physics is that these magnetization fields should not be a local function of the GFF, unlike this polarization thing. And if you think about it, we have a coupling of the GFF with the Ising magnetization field, but the Ising magnetization field is defined using level sets of the GFF. And even if you have a function to say what its level sets are, it's not a local function of your global surface, okay? To know where the level sets are, you need to know the function globally. So these fields that we define are functions of the GFF, but they are not local functions. This is in agreement with the CFT prediction, but we also realize them as true expectations of real random fields, which is not defined or predicted in physics as far as we understand. And that's it for me. Thank you. Thank you very much.
Feel free to unmute and clap instead of give the usual everything like that, which we can do. If there are any questions, please feel free to unmute and ask. Or send it in chat. Otherwise, I will ask some questions because I got a couple of things I want to know. Since I am slightly worried I might be stepping on Lorca's stuff for next lecture, but I guess the most tantalizing thing is this two different process thing where you sort of got the 2 lambda, negative 2 lambda delta, then a different, was it 2 root 2 minus 2 kind of thing, and then going back and forth in this sort of alternation. This is because things are not self-dual?
Yes.
And you sort of have like one of them corresponds to the primal and one of them corresponds to the dual process?
Indeed, exactly. That's the case. And the dual process will have a different Hausdorff dimension. And we prove our main result is in the continuum, but we prove it using couplings that we know from the discrete. And in the discrete, the process that we have, which has Edwards-Sokal property with Ising, its dual has an Edwards-Sokal property with the polarization field. So if you flip coins on the dual, you get actually for easing, it's the product of two independent easing configurations. So this should have a different scaling behavior because it should have a behavior of 1/4, just 1/8 plus 1/8. So it should have a different Hausdorff dimension. So if you think about it, you need to change the levels of these two-valued set to get a different Hausdorff dimension. So actually, there is a paper which appeared simultaneously to ours, also with one author is Thomas, and the other is Avelio Sepulveda, who did this sort of decomposition of the field into these geometric sets for in the dual picture as well for the XOR easing. But the question, yeah, it's the reason is that it's not self-dual, and for FK it's self-dual, so you have to do always the same process.
Okay. And you're not getting some free conformal invariance out of this, where you sort of have a new field and a new thing that's now conformally invariant. It's just because it's some other function of easing, which we already knew was conformally invariant. We're not. You can't cheat your way through to get something new that we didn't realize was conformally invariant out of this. Probably asking too much, but
I don't think so. It's a good question. The one thing we can say, I think Lorca can correct me if I'm wrong, is that in our proof, we only use convergence of the one-point function of the easing model,
okay.
and we don't use convergence of multi-point spin correlations. So, but that's anyway, we get, yeah, we could as well use all correlation functions, I mean, for the same result, but it's not necessary for us.
Thank you. If there are no further questions, then let's all clap again to Marcin. Thank you very much. I'm going to run to use the restroom very fast, but we'll give Lorca a second to set up and we'll be back in 5 minutes.
Marcin, can
Is it a situation where you got? Oh,
okay, so that should be fixed now.
Lorca, the screen is yours, please.
Yeah, sorry, could you just give my iPad
Yes, of course.
screen sharing privileges? Thanks.
I think that's going to work out.
Okay, great. So I will be continuing the talk that Marcin just gave, and I'll be particularly focusing on this new percolation representation of the easing model that also has this Edwards-Sokal property, but it is not the same as the FK easing model. And to start, let me just emphasize that when I say it's not the same, I really mean not just as a distribution on edge configurations, but really as a distribution on connected components. Of course, this is the thing you really care about with this Edwards-Sokal property. So I'm going to start quite basic, just by sort of recalling this object, which has been sort of central to the study of the easing model, which is the random currents. So to motivate this, let me start with a very simple computation. So I'll start just by formalizing everything. So I have my easing model. So I take G to be a finite graph. I take a coupling constant J to be positive. And then I consider the probability measure on spin configurations, which is just proportional to this Boltzmann weight sum over the edges of my graph, and then this 2-point nearest neighbor interaction for spin configurations. So assignments of plus and minus 1 to each vertex of my graph. And given this easing model, this is my probability measure. And what should I normalize by? Well, it's an object called the partition function, denoted Z. So this is nothing more than the sum over easing configurations of this easing weight. And to motivate random currents, basically what I'm going to do is just a very simple Taylor expansion of this thing. So if I write this now in the following form, so instead of a sum, I have a product, then I can Taylor expand. I get a sum for each edge over the natural numbers of the following quantity. And I can now regroup these terms. So I regroup these terms, and that gives me an object called a current. So a current is just an assignment from each edge of my graph to the natural numbers. And each current gets a weight, j to the n over n factorial. So that's for each e. I get this weight. And then having interchanged the sums, I finally have this sum over sigma of this factor, which is sigma u to the power of the degree of the vertex u in my current. So here, I'm just using this notation delta nu. This is the sum over incident vertices of my current, so the total degree. And the sort of crucial observation now is that this quantity here is exactly equal to 2 to the number of vertices if delta nu is even for all u. But on the other hand, it's just vanishing by the symmetry of the, I'm just summing over uniform configurations. So it just vanishes if this constraint doesn't hold. So if I introduce this notation delta n, this is exactly the set of u where delta n is u is odd. And what I've just said is that this contribution is vanishing if this set, which we denote the sources of the current, is non-empty. So this very simple expansion motivates me to do to introduce the following definition. So I introduce a probability measure which is proportional to this weight that we had before. So J to the NE divided by NE. It's a sort of a Poissonian weight. And then I have the indicator function that my current is sourceless. So that's exactly this contribution here is non-vanishing. And this is the random current model. So why is this object interesting? I guess the most central feature about it is something called the switching lemma. And that plays a key role in our proof too. So the switching lemma is the following observation, is that if I look at my Ising model and I look at this 2-point correlation function, then I can instead write this as the following probability. Sorry, I should say here that this measure here, I denote it with a subscript G for my graph and with an empty set in the superscript to denote that the current is sourceless. Then this correlation is exactly the probability under a doubled system of currents. So here I take two independent currents, N1 and N2, and I look at this connection event in what's called their trace. So here N hat is just the subset of edges in my graph, which have non-zero current. So it's just a simple way of transferring a current into a percolation model. And if I do this with this doubled system, so this is the double random current, then I have a way to rewrite Ising spin correlations as this percolation type event.
I guess,
And of
Lorca,
course, I'm missing the
you mean
key
this
square here. Yeah, of course. So that's the central part of this switching lemma. So this was, I guess, studied by Griffiths, Hurst, and Sherman in the 1970s. And since then, random currents have had a very strong influence on the study of the Ising model. There are just some applications. And the first one is this notion of triviality. So I think Marcin touched on it a bit, but that's this notion that in higher dimensions, so d larger than 4, this object we're looking at, which is the scaling limit of the Ising field, is just Gaussian. So this was proved by Eisenman and also by Eisenman and Domino-Copan. And the second application is continuity in d equals 3. And this is Eisenman, Domino-Copan, and Siderovicius. And all of these applications use random currents in a really central way. Okay, but we're going to take a sort of new perspective on random currents now and introduce basically a new percolation model, which can be defined through this random current perspective. So that's what we're going to do now, is a new percolation model. And the way we do this is the following. So we're going to suppose that G is a planar graph. So by planar graph, I just mean that it can be drawn in the plane like this. And to any planar graph, I have what's called the planar dual. So this is the graph whose vertices are the faces of my original graph. The faces of the dual are the vertices of my original, and then the edges are in bijection with one another. So this is my graph G star.
I think we lost your screen.
Yep, sorry about that.
There we go.
Okay. So this is the planar dual. And now I just need to introduce a little bit of notation. So given any subset eta, so eta will be a subset of the edges of my dual graph, I'm going to let eta star to be a subset of the edges of my original graph, and it's given by the following thing. So I take each edge of my dual graph if and only if its corresponding dual edge is not in eta. So as I said before, each edge of my original graph has a corresponding dual edge, and this exactly defines me a percolation model on the original graph if I'm given one to start with on the dual graph. And that's exactly what we're going to do. So now I'll define this percolation model that we've been talking about. Actually, I'll give two definitions. So this is definition one, if you like. And the idea is to let n be the double random current on the dual graph. So I'm going to sample this on the dual graph with the weight that I described above, and that's with coupling J star. So as Marcin briefly mentioned, there is this correspondence of the coupling graphs with plane duality of the Ising model. And so here, if I start with an original J, then I'm going to look at the double random current with J star coupling. I mean, if these couplings are self-dual, then you don't need to worry about this, which is basically the case we consider. So n is the double random current on the dual graph, and I'm going to define our percolation model, which we call omega. So this is going to be exactly n hat. Recall this is a percolation model on the dual, and then I take its dual. So this is now a percolation model on my original graph. So this is the percolation model that we'll be considering. And the main reason we're interested in is the following result. This is in the paper, is that if I look at spin correlations of the Ising model, then these are now translated into connectivity events for this percolation omega. And here there is no square. So it's really just the Ising spin correlations are connectivity events. And so just a few remarks about this. So this is actually I've stated it here for the 2-point function, but it really extends to all k-point functions. And actually it's a new Edwards-Sokal representation of the Ising model. So by Edwards-Sokal representation, I mean that if I start with this percolation model omega and assign independent coins plus and minus 1 symmetrically to each cluster, then I result in a spin configuration which exactly has the law of the Ising model. And this relation here between the 2-point function is just one consequence of that. And you can see that just by simply the fact that if the two vertices x and y were to live in different connected components, and conditionally in this process, they would of course have independent spins, so their correlation would be 0. And what's surprising really is that this is an Edwards-Sokal representation that's different from the FK Ising representation. So this representation, the FK Ising, has been very well studied. And if you've never seen this before, it's perhaps even a bit surprising that the Ising model has two different representations like this. But as Marcin says, it actually has many. So here we have a very natural example of an Edwards-Sokal representation. And actually, it generalizes in many ways. So the first thing is that it generalizes to the non-planar case. It also generalizes to this Ashkin-Teller model that Marcin briefly introduced, and to many other situations. So different boundary conditions, plus boundary conditions, and this kind of thing. So this is the percolation model that's really underlying our result. So we will take a scaling limit of this coupling, basically, and get a new coupling in the continuum between this Ising magnetization field and the geometry of the scaling limit of this percolation. So I'll talk a little bit about that later.
May I interrupt for just a second?
Yeah.
If you're not planar, how is this even defined? There is no planar dual.
Yep. Let me get to this second definition.
I'm jumping ahead of myself. And
no, it's a good question. Yeah. So I mean, Yeah, you cannot give this definition as easily in the non-planar case. But there is a second definition. So this is now, I will be talking about this Edwards-Sokal property. So to introduce the second definition, I just need some notation. So given a spin configuration, I'm going to let psi of sigma simply be the edges in my graph on which the spins agree. So this is the set of agreeing edges in my spin configuration. And I'm going to also write capital P subscript lower p for Bernoulli bond percolation on G with parameter P. And I will sort of abuse notation here by using this notation both for the measure itself and for a random variable sampled from this measure. And so there is a classical fact about the FK Ising model that if I look at psi of sigma intersected with this Bernoulli bond percolation, and I take P to be related to J in the following way, then this actually has the law of FK Ising. And the second definition that I'm going to give is going to be very reminiscent of this, basically. So let me give my second definition. And as you'll see, nothing I'm using here is referring to planarity. So that's why this definition extends to this non-planar case. So I let sigma and sigma prime be now two independent Ising models. And they are sampled with the same coupling constant J. I'm also going to let Q be now this parameter. So this is 1 minus e to the minus 4j. So note that it's not quite the same as the P we had before for FK Ising. And then the claim is that this distribution of omega that I introduced before has the same distribution, or if you like, is another definition, as the following object. So this is this intersection of psi of sigma with psi of sigma prime and this Bernoulli bond percolation, which is taken independently from the Ising models. And so what is this process here? Basically, I look at my graph and my two spin configurations. And if on that edge, one of the spin configurations does not agree, then I don't look at this edge at all, basically. On the other hand, for the edges on which both spin models agree, so they're sort of in their maximal or minimal energy state, then I keep that edge with a certain probability, which is given by Q. And I don't require the spin models to agree with each other. They just have to sort of agree within each other on that edge. So this is my second definition. And what I'm not going to do today is talk about why it actually gives the same result as the first definition. But I can just say, maybe if you know a little bit about random currents, that say this object here, so this psi of sigma, this is just the joule of the odd part of a single current. So this here is an intersection of three objects. So you imagine that the joule is a union of three objects. Actually, this first one will be the odd part of the first current. The second will be the odd part of the second current. And then the third will be the remaining even part, basically. But as I said, I'm not going to give a formal proof of this fact that it gives the same in the two definitions. But using this definition now, my goal now is to prove this Edwards-Sokal property for omega. And to do so, we have like basically a fundamental lemma, which I think is very nice. It's quite reminiscent of the switching lemma, actually. So this says the following. So let sigma and sigma prime be independent Ising, so exactly as above. And I'm going to consider their product, tau. So this has the law of the XOR Ising model. And the statement of the lemma is the following. It says that given tau, so I look at the conditional law conditioning on this product. And sigma actually remains an easing model, but it's restricted to this subgraph psi of tau, and now with coupling 2j. Okay, so I will start the proof immediately because I think the proof is a better indication of the statement than the statement itself is. So the key thing to do is just to look at this joint density of sigma and sigma prime. And of course, it factorizes, but I can write it in the following way. And then the observation is just that this here is exactly equal to twice the indicator function that tau agrees along that edge, and then the sigma u, sigma v easing style interaction. So all I've done here is just rewrite this as an algebraic identity, but it's clear now that if I condition on tau, then sigma is left being an easing model with these, if you like, random coupling constants. So they now vary along each edge. It's an inhomogeneous easing model, but actually they're either 0 or 2j, and whether they are 2j just depends on whether this edge lies in this subset psi of tau. So this is the sort of fundamental lemma, I think, behind this Edwards-Sokal property. So using this, I will now prove this Edwards-Sokal property. And the proof is quite short. So the first thing to do is just note, so omega, recall, has this distribution of psi of sigma dissected with psi of sigma prime, and this Bernoulli with parameter q. And just a simple rewriting in the following way, I keep my psi of sigma, and now I look at psi of tau. And the reason this is true is that if the two spin configurations agree, then this is equivalent to one of the spin configurations and their product agree. So given this rewriting, the crucial thing to do now is to condition on tau. And look at these objects. So let's just look at this first object. So first, as we know, as we said, psi is now easing on this subgraph, psi of tau, with parameter 2j. So that's exactly this fundamental lemma that I said before. And now what's this other object? So this now, if you think about it, so psi of tau intersected with Bernoulli with parameter q is nothing more than Bernoulli bond percolation again, now with an inhomogeneous parameter given by, that depends on tau, given by the following. So 1 minus e to the minus, and I write it in the following way, so minus 2 times 2j, the indicator function that tau u is tau v. So just note that if this indicator function is 0, then this probability to be open will be 0. Okay. And actually, these are basically the only two ingredients you need, because after this, we see that conditionally on tau, omega is the sort of FK easing representation of sigma. So you should compare basically these two facts with this fact that I gave about the FK easing model here. And note here, this parameter p, it was basically given by 1 minus e to the minus twice the coupling constant. Here, these coupling constants have 2j essentially. So here we have twice 2j, which is exactly matching this factor 4j that I had in my definition of q. So conditionally on tau, omega is the FK easing representation of sigma. And so in particular, has this Edwards-Sokal property, again, conditionally on this product. But actually, since this is a statement about distributions, it also holds unconditionally. So for example, this tells me that if I look at this 2-point function, and this is just the probability that they're connected, again, conditionally on tau. No, sorry. This is not. Yeah, sorry. This is the connectivity function conditionally on tau, but of course I can just integrate this to say that it's holding unconditionally. So this actually also holds unconditionally. And that gives the proof that this model has the Edwards circle property, basically. Yeah. So this is the percolation model that we're going to be using, and this is why it has the Edwards circle property, basically. Okay. So if there are no questions about this, then I will continue on to the next part, which is a sort of overview of this of our proof. So and the question really at the heart of this proof is the following: can we actually translate this coupling? So this Edwards circle property gives you a coupling between an Ising model and a percolation model. And can you translate this coupling into the continuum? And that's really the problem that you have to solve if you want to end up with this coupling between the Ising magnetization field and the Gaussian free field. So I want to talk a bit about why this is a difficult problem, basically. But let me just first set up what we do know. So the setup, as Marcin sort of briefly introduced, is that I take a fixed domain in my plane, and I have this mesh size, delta, which I imagine is very small. And I'm looking at this domain with very small mesh size. So I consider sigma delta. This is this Ising model on d delta, which is just the intersection with my square lattice of mesh size delta. And I look at it at criticality. So at this critical value of the coupling constant, which is known to be the following. So this is the setup. And then I also have omega delta. This is my percolation model. And what's really of relevance in this Edwards circle coupling is the law of the connected components. So let me denote by C delta K to be these connected components. So I index them here in some manner. Perhaps you choose decreasing in diameter. So these are my connected components of omega delta. And what do we know? So the first thing we know is the following. So we view sigma delta. So this is a spin configuration. We view it as a field. And we do that by using a test function. So suppose we fix some function f, which is, you can take smooth to be like. Then we have this testing of this function against sigma delta, which we define in the following way. So all I've done here is introduce this correct scaling such that this thing is of order 1. So I have a delta squared here because I have a delta to the -2 number of lattice points. And then I have this delta to the -1/8 to counteract this one-arm exponent of the Ising model that Marcin introduced. So each, on average, these spins have a magnetization of order delta to the 1/8. So then it's actually known, so if I view it in this manner, so it's known that these observables converge in distribution to this IMF tested against this function as delta goes to 0. So as Marcin said, this follows from work of Chelkak, Ongler, and Izurov in 2012, but I think was sort of first written down in this work of Kamiya, Garban, and Newman in the same year. And this is really the IMF. So this is the definition, if you like. So somehow the convergence of the easing, which is sort of one marginal of the coupling, is known, and we can, if you like, take that for granted. Okay, but what about these clusters? And actually, it turns out that we know the convergence of them as well. So actually, we know that these clusters converge as delta goes to 0 for all k larger than 1. And this is work of Hugo Domino-Copin, Marcin, and Wei Chen. Recent work. And the reason why we know this convergence is because they proved convergence of the double random current. And since our model is the planar dual, it's very easy to translate this into convergence of our percolation model. Where do the clusters live? They essentially live exactly where the clusters of the double random current don't live. So these sets, so these are CK. So these sets are exactly these sets that Marcin was introducing, and they can be, if you like, extracted from the GFF through this exploration procedure. These are these carpets of the C84. And they are random closed sets with this correct Hausdorff dimension. So this dimension 2 minus 1 over 8. So this bit, you don't have to work very hard to get. So basically, you have a coupling, you know each of the marginals converge. And so the central problem is this the joint law of them converging in the right way. Is it giving you the right thing in the continuum? So I just have like basically a little example of what's the problem is here. So this is our domain D, has this mesh size delta. And suppose that there is some box, I'll call it B in this domain. I fix a box B, and I let my test function simply be the indicator function of this box B. Okay, this is not a smooth function, but it doesn't matter, basically. So then when I look at my easing field tested against this indicator function, it's nothing more than the average magnetization of this box. So yeah, exactly. I'm summing over the points in my discretization of the box. I have this factor delta to the 2 minus 1 over 8, and then the easing model. So this is the magnetization of the box. Okay, so this is an object that we understand very well, basically. And by this Edwards-Sokal coupling, we can rewrite this in the following way. I can rewrite sigma delta of x as a sum over the clusters of my percolation model. I have a sign, independent sign mu k, and the indicator function that this is x belongs to that cluster. So here, these are just IID plus minus 1 signs. And this is a sum, but really it's not really a sum because only one of these terms will be non-zero. So this is simply just a rewriting of this Edwards-Sokal property. And using this, I can rewrite sigma delta of f to be now the sum over these clusters. So I've just interchanged the sums here. I have this sign mu k, and then I have the sum over the points in my box, delta to the 2 minus 1 over 8 k function. And of course, this I can just rewrite as delta to the 2 minus 1 over 8. And the size of the intersection between the cluster and this box. So if you like, I have my box here. And what I'm interested in, this magnetization, it turns into a sum over each cluster of the size of this intersection. So it's really these intersections, these areas that you need to understand. So what's the problem, basically? So the problem is the following, is that sort of know that these clusters are converging to these continuum clusters. And this convergence is in Hausdorff distance, so as closed sets. But of course, this is not implying the convergence of these quantities. So if you like, the area of the cluster. And actually, this is quite a subtle issue, right? Because these continuum clusters, we know they have zero Lebesgue measure, so there has to be something going on, and we expect the limit to actually be this conformal Minkowski content of the clusters that's not known to exist, but we expect limit to be basically this an appropriate notion of an area measure on this cluster. Okay, so basically the emphasis here is that I can rewrite easing observables as sums over clusters and treat each cluster separately. But what am I left with? I'm left with basically the area of these clusters in certain subsets of an domain. So this is the thing that I need to understand now, basically. And I'm going to talk a little bit about the strategy that we use for dealing with this. Because this is not the first time that this problem has been encountered, of course. And the strategy we use is really inspired by this work of Gabin, Pete, and Schramm, where they sort of studied a similar problem for Bernoulli side percolation on the triangular lattice. And the idea is the following. So basically, we don't know anything about the convergence of the area, but we do know that if I just look at whether the cluster intersects the box at all, basically asking, is the area positive, then we do know that these indicator functions are converging to the same for the continuum clusters. This is just a simple consequence of the Hausdorff convergence, basically. So this is like, if you like, a very crude approximate of the area. So we can't study the area, we can only say whether it's zero or positive, if you like. And the strategy really is to do better than this. It's sort of a very natural one, basically. So what we do is we take epsilon, so this is another parameter, and we take it in the following regime. So we take it much larger than delta, say, but still going to zero in the limit. And we look at our box. As I say, we have a cluster which we know intersects it. Then we introduce essentially an epsilon tiling of this box. So we tile the box with squares of side length epsilon. And instead of counting the area, we just count how many of these boxes actually intersect my cluster. So here, I would basically be taking all of these boxes, maybe this one, like that. Okay, so let me introduce this notation. So I call y delta epsilon. So this is the number of epsilon boxes in B which intersect C delta K. And the hope then is that we can do much better than this crude approximation before, and actually hope that this area is very well approximated by this approximate. And I've introduced this factor epsilon to the 2 minus 1 over 8 here. So why have I done this? I should maybe say that so both terms here on the left and right are actually of order 1. And the reason to see this, as I said, so for a given site, so on the left-hand side, the probability that a given site lies in a macroscopic cluster, basically. I mean, this is essentially this one-arm probability that my site is connected to a distance of 1 over delta, which, as we know, is this factor delta to the 1 over 8th. On the other hand, for a given box, so maybe here I call one of these boxes A epsilon, then the probability that A epsilon intersects my cluster is now approximately this one-arm probability, not started from a single site, but started from a box to one other box, so essentially in an annulus. And on the lattice level, this inner box basically has size epsilon to the delta -1, and the outer box needs to reach a macroscopic distance, so it's of order delta to the -1. And using this theory of quasi-multiplicativity, I see that this should be scaling as epsilon to the 1/8, basically. So this is this notion of quasi-multiplicativity. And so exactly these exponents are matching. And so both of these terms here are of order 1. So they're sort of exactly renormalized such that they're going to be tight in the scaling limit. And so this is our hope now, that we can prove this approximation. And actually, I should say why it implies the desired result. So actually, it proves the result because the limit of epsilon to the 2 minus 1/8 y delta epsilon as delta goes down to 0 is sort of easy to understand. So for a fixed epsilon, this observable is nothing more than a sum over indicator functions. And as I said, that we know exactly from this very crude strategy that these indicator functions are converging just by the convergence of these clusters. So if we can hope to prove such an approximation, it actually implies the result that we want, which is eventually leading to this coupling of the Ising magnetization field. Okay, so how would one even hope to prove such an approximation? Well, actually, we do. So this is the following theorem. And it says the following. So if I look at these two quantities, so there exists some beta positive. And on the left-hand side, I have my intersection of the cluster with the box. Then I have beta times exactly the right-hand side, which is this number of epsilon boxes intersected. And as a random variable, this is going in a sort of L2 distance to 0 as I take first delta to 0 and then epsilon to 0. So this is the result that we want to prove now, because this is allowing us to sort of show the convergence of these discrete measures to their continuum counterparts. Okay, so how the main idea to prove this result is the following. It's a sort of very natural thing once you realize it, but I focus in on a single box, and I have my cluster living here, and okay, this is all living within some one big box P. So I rewrite my area as a sum over these boxes, just of the area in that box. So that's very simple. So this is the sum of terms now, and sort of there are two inputs that you need. So you first want to say that each of these terms is roughly independent. So there is a sort of spatial decorrelation going on. And that's the way you do that, and the sort of second ingredient is that you really want these terms to concentrate highly around their mean. So actually, what the idea is to do is to first say that this expectation of these quantities, crucially conditioned on them being non-negative, conditioned on them being positive, sorry, is equal to some factor beta. So this is this parameter beta that I introduced before, and it's universal if you like, so it doesn't depend on anything. And this is this sort of first mean estimate. And then you would like to say that actually these quantities concentrate very sharply around this value. And why does this tell you? So if you knew concentration, then I can rewrite this sum over here as essentially with a little error factor, exactly beta times sorry, this should be an epsilon to the 2 minus 1 over 8 here. So the exactly this approximate, basically. So this is the goal, basically, to zoom in on a single box and to say that the cluster inside that box, its intersection is concentrating very sharply around its mean, and in particular is very independent from what's going on in other boxes which are far away. Okay, so why would you even expect this sort of concentration? Well, the idea is to basically think what is the cluster behaving like inside this box. So given that it hits the box, it has some distribution, and the idea is to sort of precisely say what is this distribution. So the idea is the following, which I think is very nice, and that's a macroscopic cluster conditioned on hitting this box behaves like something called the IIC measure. So IIC here stands for incipient infinite cluster. And this is basically, well, I can give you a definition of it now, basically, but it's exactly describing this behavior of macroscopic clusters once you condition on them being in a certain region. But actually, its definition I can just state very simply. So here I return to the sort of full plane setting, if you like, a mesh size 1. So the IIC is the measure, which I put in quotes for now. And it's exactly the measure conditioned on the origin lying in an infinite component of omega. So actually, we know that in the unconditioned measure, this will never happen. So continuity of the Ising model in 2 dimensions tells you that this conditioning is singular, basically. So one has to make sense of this quantity, which I put in quotes. And the way to do that is to write it as a limit, basically. So one needs to show that if I condition on it being in a cluster of larger and larger size, then this limit is actually converging. And the limit then is what I call this IIC measure. So constructing this IIC measure is basically the core ingredient in proving that this macroscopic cluster behaves like it, and therefore proving this concentration, which in the end is implying the result. Okay. So constructing this IIC measure is a sort of task on its own rights in planar percolation. And yeah, basically, I mean, it's a non-trivial task. So you need to prove it exists. So for instance, unlike the unconditional infinite volume limit, where the limit is easy to see, maybe you have some monotonicity or something that's telling you that there's a limit to this unconditioned measure, which we sort of take for granted nowadays. Here, there is going to be definitely no monotonicity in this limit. But just to prove it exists is a non-trivial task. And so that's what we do for this omega. And the main ingredients we need are the following. So the ingredients, the first one is a sort of RSW type crossing estimate. So as Marcin said, we prove these RSW estimates for this percolation model. And also we have to deal with the following very annoying fact, which is that omega has no FKG. So as a percolation model, it does not satisfy the FKG inequality. However, what we do is the following. You can actually decompose it into 2 percolation models such that it becomes their union. And actually, these 2 percolation models have FKG. So I think this is a very nice trick that we use a lot in our arguments to get around, to circumvent this fact that there is no FKG for the single percolation model. And in this context, it was introduced by Glasman and Lammers, who showed that there is this sort of partial or split FKG, if you like. Obviously, these 2 percolations, omega plus and omega minus, are not independent. But it actually turns out that they are negatively correlated with each other. Okay, so these are the ingredients we need. We need an RSW crossing estimate, and we need to work around this lack of FKG. But this is what we do, and this is the core of our article, is to construct this IAC measure, and as I said, to then show that it implies that this coupling is surviving in the limit. Okay, so yeah, I think that's actually everything I wanted to say. So thank you all for listening.
Thank you, Lorca. Again, unmute and clap, please. I'll do it in the name of everyone who's does feel uncomfortable with that. And of course, if anyone has any questions, please feel free to unmute yourself and ask or put it in chat.
May I ask one small question?
Of course, please.
Yep.
Thank you. It was a brilliant both presentations. My question is there any relationship? I assume this is in dimension 2, everything, or could it work in dimensions higher than 2? You mentioned planarity, but this is planar graphs and something different, right? Thanks. Just interested.
Yes. So this new Edward-Sokal representation, this does extend to any graph. So this doesn't require planarity. But the core of this result, which is this continuum coupling between the Ising magnetization field and the Gaussian free field, I mean, this is really built on this picture of bosonization. So I don't believe there is any conjecture on how any sort of coupling like this should behave in higher dimensions. So this is, I mean, the Ising model in the planar setting has very special properties that are just not available when you move to higher dimensions.
Okay, thank you.
Thanks. Anyone else before I start doing my thing? Because I've got this. So I was just very struck because your omega seems to be a mixture of FK Isings. Is that right? The idea is that conditional on tau, this is just FK Ising, and in homogeneous FK Ising, but an FK Ising nonetheless, and then you average over the tau measure to get that.
Yeah.
And each of those FK Isings is perfectly FKG.
Yes.
Obviously, that doesn't mean the mixture is FKG. We know that these things don't survive linear combinations, but like things like the existence of this limit, isn't that for free? Just condition on tau, take the limit, and then average? Because you do have FKG, so just the fact that this is like you can sort of do that. I mean, I'm not saying this like omega plus omega minus. It just seems that the fact that this is an annealed model, that when you quench it, you lose translation invariance, but that's fine. This is already not translation invariant, but it seems like you have a huge thing here in the fact that this is an annealed model of something that's the quenched FK Ising model. Like condition on tau, everything seems very, very nice. Outside of the fact that you break symmetry. Yes, and this is a me question. I understand that this is the me playing up to every possible stereotype of myself.
Yeah, right. So I mean, you're exactly right. So I mean, first this decomposition, it's probably obvious to already, but so these quenched FK Ising models. So we know the FK Ising model is increasing in the parameters. But the parameters here are governed by this agreement graph, so this psi of tau. So psi of tau is not increasing in tau, unfortunately.
Okay, so that's the issue. I understand.
But what you can do is say psi of tau sort of splits into the edges on which both spins are plus and the edges on which both spins are minus, right? And so this is really where this decomposition is coming from. But you're sort of right in a sense that you're not very far from FKG. So that's actually how this proof of IAC goes. So yeah, we're basically using this FKG and just always sort of having to deal with the fact that it's not quite FKG. But yes, you're sort of close to FKG in a sense. Yeah.
Cool. Okay, if there's no one else, again, thank you very much to both speakers. This was lovely. So all applause and that. And the next meeting of the One More Probability seminar will be 3 weeks from today on April 9th. I hope to see everyone there. And yeah, I'll see you guys then. And let's